It's a pleasure to be here. I'll tell you today about a topic that actually has been in my head since I was a graduate student. And I think I at least have resolution. we'll see if the community will agree with me at some point. So you may have heard, if you're in the compact object community, that there is a gap potentially in the black hole mass distribution, especially between 3 and 5 solar masses, between basically missing black holes on the low end of what nominally in astrophysics we label as black holes safely. Now that we have more neutron stars, the definition of this gap has extended to be down to the maximum neutron star mass, which, you know, we can take bets, but maybe it's as low as 2.5. But that's the gap I am talking about, okay? And I'm gonna try and put together all kinds of observations, interpretations of observations that in isolation, they all make sense, but together they don't. And then I'll share with you what we think is going on. All right, so where can we measure black holes? Well, for the longest of time, I keep forgetting I don't have a laser pointer. So let's see if I can stay behind the podium. So for the longest of times, we could measure black holes only in X-ray binaries. So black holes accreting mass from companions. Lately, we can measure black hole masses in wide binaries discovered with GAIDA. And somewhere in between these two time periods, we can also measure black hole masses in mergers of black holes with other black holes or with neutron stars through gravitational waves. I don't have a picture for binary black hole mergers because it just, in this sequence, it's just 2 black dots on the screen. But here they are. All right, so just to remind you, there are 2 types of X-ray binaries. Low mass X-ray binaries and high mass X-ray binaries. This refers to the companion of the compact object. In this case, we're focusing on black hole X-ray binaries. And typically, heuristically, and historically, low mass X-ray binaries are those that have donors less than 2 solar masses, roughly, and they are fed through Roche lobe overflow. And high mass X-ray binaries have companions that are more than about 5 solar masses, and they are fed by the stellar wind of the massive star. Part of it is being captured by the black hole. And in both of these kinds of systems, we are able to measure the black hole mass. Now, I'm going to start with some gap history. And the first plot I'm going to show you, I promise you it's the worst plot throughout the talk. It's not my plot. It's from a paper back in 1998 when I was the first year postdoc or a finishing graduate student by Charles Bailyn and collaborators. And they were the first to point out, argue that the black hole mass spectrum of the time had missing low mass black holes. Now, like as smart as I was back then, I met Charles on a job interview and I made fun of him. And I said, Charles, come on, how can you be arguing this? It's ridiculous. The only way you can argue there is a black hole is it is at 50 percentile confidence level that there is a black hole mass. So this is low mass black holes, upper mass black holes for the distribution. And at 50 percentile, the low end of the black holes is at 2 solar masses, somewhere between 2 and 5 solar masses. And here it is with removing some system. The low end is between 4 and 5. And this is it, the 50% between 4 and 5. But if you go to 95%, you go back to 2 solar masses. So based on that, the paper was written, we have a crisis, missing black holes at low masses. And I laughed because I was a budding statistician. Well, he was right. So let's hold that thought in 1998 in our heads. Okay, so the gap was claimed based on that data. Moving forward, I'd like to also make sure everybody keeps in their mind that low mass X-ray binaries are actually the vast majority for the ones we measure black hole masses. They are X-ray transients, and that's important for our story. So here's behavior of an X-ray transient. How do we discover them? Basically, they become extremely bright in X-rays. This is a logarithmic scale. And then over tens of days, most of them, not all of them, they decline in X-ray luminosity, and many of them completely disappear. But that's how we find them. Okay. Now, when I'm coming ahead of myself, but this is important for how we measure black hole masses. This is basically a thermal instability. It has to do with the ionization of hydrogen in the disk and how mass transfer actually works in these systems. And mass transfer is episodic in these systems through this thermal ionization instability. You can look at observations of lots of these, and heuristically and potentially and by eye, you can say that maybe one can develop a model and model the time behavior of this flux, the X-ray flux, the way you see it here on the plot, roughly. Okay, so these predictions there are coming from the thermal disk instability model for X-ray outbursts, and it kind of does a good job also explaining a few other characteristics of the systems. Now, the transient behavior, as I told you, is necessary for us to measure the black hole mass, and this will be important almost throughout our discussion. This is young Wilfar when he joined my group as a postdoc from MIT. So we'll come back to this guy. So what's needed for us to have a dynamical mass measurement is we need to measure basically the motion of the companion. And in order to measure the motion of the companion, we need to be able to detect the companion. This is low mass X-ray binaries. The star is 1 or 2 solar mass at best. Maybe it's a half a solar mass, so it's not easy to detect. When the X-ray binary is in outburst, not only the X-rays are very bright, but also the disk is very bright. That's when accretion is actually happening. And the disk emits a multicolor black body. And it actually is quite bright, even at the wavelengths that you would expect a low mass star to be bright, and it masks the low mass star. So you cannot track the low mass star. You cannot do any dynamical and radial velocity measurements in optical or infrared. So you have to discover the low mass X-ray binary in outburst, and then you have to wait how long it takes for the low mass X-ray binary to become quiescent again, undetectable in X-rays, undetectable in disk emission. Then you find the companion, then you go about your dynamical measurements, okay? So if you do that, and if you're lucky enough that your X-ray binary not only gets discovered in outbursts, but also does you the favor of going into quiescence during human lifetimes, then you can do this measurement. And people had done this for a number of X-ray binaries at the time. And these are the measurements that Wilfar and I used many years later, from 98 to 2011, to do an analysis of the black hole masses of these systems. Okay, I'm not telling you what was the result of the analysis in 2010. I'm going back in time again. Bailyn has made his claim. Most everybody believes him, by the way. I don't. And then back then, 2001, postdoc, another postdoc, Chris Fryer, also now senior person at Los Alamos, he and I decide to look at core collapse simulations and their results about the masses of compact objects and fold it in with different types of IMFs and different different modeling of how binary evolution might change the expectation of the mass distribution of compact objects. So we work out a number of different things, and we have mass functions, predicted mass functions for compact objects. That's 2001. And basically we write and what if this and what if that. It's a very long paper. And we keep saying there is no gap, that we can't see any reason for a gap. No matter what you do, change the winds, change binary evolution, etc. And we're comparing now to the individual measurements of the black holes known at the time. But then we say, Bailyn is claiming a gap. How can you get a gap? We said another possibility is that some observational selection effect is working against low mass black holes. Maybe the transient character is their problem, and maybe a selection effect is connected to the transient character. And then we go on and we go on and we find ways to create a gap. And we said such a gap could place strong constraints on the supernova explosion. So basically, we looked at what would create a gap in the birth masses of black hole. And we concluded at the time, the only thing we could find in the analysis we were doing is if, one way we said, is if the explosion energy of the supernova, of the collapsing core, behaves as a step function, as a function of the progenitor mass. If you have some dependence, actually this way, the more massive your star is, the weaker is your supernova explosion, but at some point it plummets. And if it's a step function, it's gonna create a gap. Because now you're gonna go from forming iron core collapse, neutron stars up here. It's gonna, the energy is gonna plummet. You're gonna get a lot of black holes suddenly in the mass function, and you're gonna jump from neutron stars all the way up to something massive. And that will give you a black hole in the mass distribution. Okay, then we also artificially put it in, artificially, no physics here. And we created a black hole. And we said that's how you would get a black hole. And we concluded, but there is no reason why the energy explosion would be a step function instead of a smoothly decreasing function of the progenitor. Now we go back to Will. So now it's 2011. We're working independently from the group led by Ferial. And it's now we have a bigger sample of black hole X-ray binaries with measurements. And both Ferial and her group and Will and his group with me involved at Northwestern ask the question, is there a black hole mass? But with a much more careful statistical analysis than Charles. Long story short, our approach was to ask the following question. With the full uncertainties, the PDF uncertainties of each individual measurement, can we extract a global probability distribution function for the black hole masses? And once we have those, can we extract a probability distribution function on the mass that is just at the 1% probability distribution function of the whole population? There's a lot of probability distribution function coming out of my mouth. Okay, so in a way, we're calculating for different models what is the minimum black hole mass. And it's not a number, it's a PDF. It has uncertainty. So for different models, 10 models, we're calculating the PDF of this M1%, okay, as the minimum mass. And basically, no matter what, we find it to be greater than 4.5 solar masses instead of 3, as it should be, because that's the definition. And Ferial, with different methods, finds it to be a minimum 5 solar masses. And then, since we did the analysis, we got convinced that there is a gap. Okay. Now, since now, and with these two papers, now it's a widespread accepted phenomenon. There is a gap. Now we go back to theory. Does the theory predict that there is a gap? It doesn't. There is no prediction. Now, when I ask this question to my group 6 months ago, 2 years ago, during the pandemic, everybody responds to me, to my own group. Yes, of course theory predicts there is a gap. There are the papers from Chris Fryer and Belczynski in 2012. They predict a gap. I was a co-author on those papers. We didn't predict the gap. Those papers were 2012, 2012. What we did, Chris went back to our idea from 2001 and said, damn it, the gap exists. So how are we gonna create it? We're gonna create it by creating a step function in the explosion energy as a function of progenitor. But now we understood a little bit more about the physics of supernova. We understood about what instabilities get created, what's going on with the shock, the standing shock before the explosion actually gets driven. So there was actual physics. And in that paper, Chris put together a collection of newer simulations and argued that there is an instability, it's a convective instability. We don't know what drives it. We don't know how long it lasts, but if it lasts a short amount of time and then the explosion goes, then you'll end up, for reasons I'm not clearly explaining right now, happy to do in a question, then you're gonna get a step function in the explosion energy as a function of progenitor. If the instability lasts for 200 milliseconds instead of 10 and beyond, you will have a smooth reduction of the explosion energy as a function of progenitor. Exactly what we were discussing in 2001. But now there was a physical potential explanation. We don't know which of the two is true, said the paper in 2012. But clearly, since there is a gap in the data, the rapid model is favored. That's not a prediction, of course, you understand. So that's where the birth of these famous, for those who are in the compact object community, the rapid model and the delayed model were born. And then in a follow-up paper within months, here's the gap. Okay, if you impose the conditions for the rapid supernova explosion mechanism, you get a very nice gap in the black hole mass distribution between about 3 and 5-ish solar masses, the red curve. If you use the delayed, you get no gap. You get a smooth distribution. That's it. From 2012 up until even now, every population synthesis model you see in the literature, including from my group, includes only the rapid model. There are no low mass black holes in the populations by construction. When I reach that point with my group, then I stop and I give them a little lesson of how science works. I'm not going to do this here. Where are we today? Here's a collection of black hole masses from all electromagnetic binaries and some neutron stars. You see the labels. Down here, we have the neutron star masses from pulsars, neutron star masses from Gaia. This is, I'm sorry, I forgot the reference here. I said I should put it and I forgot. This is from one of Karim El-Badri's papers. It is from the paper that reports these neutron star wide binaries, okay? So he puts together everything. These are the neutron star. These are the red, are the black holes from X-ray binaries, a lot more now. There's some spectroscopic binaries in clusters that have lower limits. And these are what the community refers to as the Gaia black holes, okay? So there's a gap, is the claim, in the electromagnetic sources. So now we're 2024, the gap persists. I will highlight these two systems. In the paper, none of the systems are named. I tried to look them up based on the collective references given in the paper. And I cannot track these two systems down. I have to email Karim, but I was putting together the talk last night, sorry. But overall, the gap is there. Now, gravitational waves. What time is it? Oh, the clock really goes down. Yikes. Okay. Gravitational waves up until recently. In gravitational waves, we measure black holes. We measure black hole masses with big error bars, and we put together population models. Here I'm talking representing the LIGO scientific collaboration, LIGO Virgo Kalogera. And when we reported on our third observational catalog, we had different parametric and non-parametric models. And basically, this is how things looked at the time. You may want to look at what happens between 3 and 5 or 2.5 and 5. And basically, don't be fooled by the lines. Look at the error bars. Basically, it's flat within the error bars, okay? So no clear evidence of a gap between 3 and 5 in gravitational waves, but the error bars are big. So maybe it's there, we just can't see it. Okay. Let's come to today. Well, not today, but you know, where are we now? With our fourth observing run, we detected this one system, which is the only system we have reported on from our fourth observing run. 0529, we're gonna call it in short. So the range for the black hole mass, we don't know it's a black hole, but it is sort of above 3 solar masses. The range is between basically 2.5 and 4.5 solar masses. The peak, 3.6 solar masses. This thing is damn centered into the low mass gap for the black holes. So no corrections for disks, light, gas, just clean measurement, okay, at 90 percentile. This is the strongest evidence we have that low mass black holes exist. I'm sorry, in the gap between 3 and 5 solar masses. When we do our all, this is the individual system. This is the black hole here, the gray band. I don't know if you can see it. This is the newly discovered system. Most of the PDF is inside the gap. You might say, oh, but there are others like this blue one, but actually the peak of the PDF is outside the gap. It has a long tail, but very little probability in that tail in the gap. I won't describe this plot very carefully. Let's come here, which is the updated population now. And now error bars are much smaller. 3 to 5 are the dashed lines. This is non-parametric, this is parametric. This even explicitly allows for the existence of a gap. There's no gap. It's almost flat. So now, where we are now is that gravitational wave data, they show no gap, and our error bars are good enough. We did another analysis with, we put together specifically binary black holes and neutron star black holes, actually only binary black holes. We discussed the cut so much. And we analyzed them exactly as we analyze the X-ray binaries, to ask if somehow the way we analyze the gravitational wave data is creating some bias, and we can't see because the population thing we don't do for black holes in X-ray binaries. So we took these individual black hole masses, we meaning current will, and and a new postdoc who joined my group. And I will not belabor the point. What we did is we calculated a simpler model to fit black hole masses in these systems. There's a lot here, but I will just draw your attention to the purple lines down to 3 solar masses. And basically, even without this new system, the distribution, all the purple lines, and this is the peak posterior probability, flat between 3 and 5. And now with this new system, definitely flat. Okay. And then we calculate the PDF of the minimum black hole. And did I put the numbers? Ah, here it is. The PDF of the minimum black hole, 3 to 3.5. We don't call anything below 3, we don't call it a black hole. So 3 is an artificial cut. So the minimum black hole for gravitational wave data is down to 3. No gap. Again, same analysis as with X-ray binaries. All right, so now where are we? Good. Black hole X-ray binaries? Definitely yes, the gap is there. Wide binaries? Probably yes, although it's hard, you know, it depends on what happens with the explosion of low mass black holes in wide binaries and whether you can keep them bound. Binary black hole mergers, definitely not a black hole. So the obvious question is, what do we do? Okay, so it's hard to, when you have an observation of a low mass black hole, it's hard to argue they're not there. So then the obvious question is, why are they not there? Okay, so that's the rest of the talk. Okay. Remember in 2001, with Chris Fryer, we said, maybe there's a selection effect hiding low mass black holes in X-ray binaries, but we couldn't come up with anything. The gravitational wave sample is corrected for selection effects. We can quantify the selection effects in the gravitational wave sample very well. They're very well understood, and we don't find the hole, even before the discovery of this one system. So could it be that low mass black holes do form in nature and do form in potential X-ray binaries, but our observations are biased against them because we have a very particular way of how we measure black hole masses in X-ray binaries. They have to be transient, they have to go up, and then they have to go down in X-rays, and then we can measure the black hole mass. So that was our hypothesis. So we worked on this question a few years back with a group of primarily students and a few senior advisors. So Jared Siegel at the time was an undergraduate at the University of Chicago working with me. Now he's a graduate student at Princeton. And Ilya Kato, undergraduate in Urbana, now a graduate student in my group. And Tom, a very well established observer of X-ray binaries to make sure we don't do anything stupid with the observations, and Christopher Berry at the time in my group. Okay, so all we did is build a population model that allows low mass black holes to form, unlike every population model in the literature for the past 10 years. And then figure out if in the models our low mass X-ray binaries are gonna be detected. So generate initial binary population, involve them, make them low mass X-ray binaries, identify the transients. We understand well enough the physics of what binary is a transient at in what part of their life. And then take into account selection effects from our X-ray surveys and calculate detection probabilities. I'm not gonna go through all of this. This gives a little more details on the method. But basically, we have to track the mass transfer. We have to track the behavior of the donor to the black hole, the star. We have to include things like magnetic braking. These are low mass stars. We have to track the transient behavior. We have to have a model for outbursts and quiescence, for duty cycles, for detectability from the detectors. That's what Tom helped us a lot with. And then our key results was, where are the low mass black holes in transient X-ray binaries? What is the mass distribution? And at the end, the key result was calculate the fraction of low mass X-ray binaries with black holes in the mass gap at any given time in the evolution of these things. One slide. We have to model the transient. It's not perfect, but this is the kind of shape we use for the transient. Most places will model the transient as a top hat, so it's on or off. We did something a little better. It's something that goes up and then slowly comes down. over what times. It depends on the black hole mass based on the understood physics. Then we also had different kinds of transitions. Here's one that's sloping and comes down like a rock, or something that's smoother. So we tried all kinds of things to assess sensitivity of these assumptions to our results. Now, what we had not thought about, but it came out in the model, is that there are two ways to populate the gap. One is you form low mass black holes from the stars. The other is you form neutron stars in low mass X-ray binaries. These things accrete for billions of years. And if the neutron star is massive enough, it can become a low mass black hole and populate the gap and create problems, fill the gap. So we keep those two in mind. So now we have two populations to track. We look at our models, and now I'm going to show you sort of punchline plots. There's a lot that I'm skipping, but I'm happy to answer questions with anything that sort of looks not making sense. We started making plots like this. F low of things that are detectable. What does this mean? First, we had our population. We reached basically the age of the galaxy. We took into account all known X-ray surveys and their sensitivities and everything. We had a model for outbursts and when are they up, when are they down. We mounted Carlod. We had a detectable, we could tell which systems are detectable for what fraction, etc. And then having that information, we calculated the fraction of systems, LMXBs, with black holes below 4.5 solar masses, i.e. in the gap. What fraction? Fraction of what? Fraction of the whole low mass X-ray binary population that is above the threshold for detection, including persistent and transients and everything. And then we started changing things. What if we use different magnetic braking? What if we use different accretion onto the compact object? Fully conservative, non-fully conservative. If it's non-fully conservative, what if it's a fixed number? What if it depends on the state, whether it's outburst or quiescent, and many more. No matter what we did, the gap was basically full. X-axis. As a function of the birth maximum mass of the neutron star. Why is this important? Because of the second population. If the neutron star is born at 1.4, which most neutron stars do, 1.4 solar masses, it never becomes a low mass black hole through the accretion history of the binary. But if it's born at 2.5, it crosses and fills the gap. So, well, I said something that's not true. Even at 1.4 in these models, it can cross. This is what the plots show. But it's a function, right? How many will cross will depend on what is the birth maximum neutron star mass you allow in your model. We were not going to set a maximum in the beginning. Once we realized that this effect exists, then we thought, oh, maybe we need to look at this. Maybe neutron stars are not born all the way to the maximum of the equation of state. So that's what the x-axis is. What is the filling factor of the gap, basically, as a function of how massive do you allow your newborn neutron stars to be? And with all the things we change, this is how we treat the shape of the outbursts, etc. What we were getting was anywhere, if you start with very low mass birth neutron stars, unrealistic, you get almost 50% or almost 100%. Same up here, 100% if you have massive born neutron stars. 50%, 60%, 50%, 60%. Clearly not what we observe. Okay. We were doing this with a very popular population synthesis code called COSMIC. Okay. Then we said, what if we do the exact same thing, but now we calculate the evolution of the low mass X-ray binary with a full stellar structure and evolution code, where we track the behavior of the star as best as we can in astrophysics, and we calculate the m dot, whether a binary becomes m dot, mass transfer rate onto the compact object, when the binary, whether the binary will become a transient or not, depends on the mass transfer rate very sensitively. If it's above a certain rate, it's not a transient. If it's below a critical certain rate, then it can have the opportunity to be a transient. So we thought mass transfer rate as a function of time must be important in these models. So then we used MESA, and through the infrastructure of a new code we're building called Poseidon. Forget about the names. The point is, here now, we're calculating the best possible treatment of mass transfer we have available in astrophysics. Here, we're comparing to our more simplified mass transfer that we use most commonly. And for the first time, we brought down the filling factor to below 20%. Okay. This stayed at 40% as for one of the models I showed you. There are models that bring it all the way up to 100%. There are no models that bring these runs anywhere above 40% out here for very massive neutron stars. And for low mass neutron stars, you're always at 20% or below. So our conclusion is that if we treat mass transfer to the best of our ability, then you can hide low mass black holes. The filling factor can go down to about 10% or 20%. Are our models perfect? Of course they're not. You know, the outburst, the shape of the outburst is the critical value for when a binary becomes a transient or not a transient, fixed for all hydrogen-rich accretion disks, probably not. But with the best physics we have right now, we can get low mass black holes to hide in low mass X-ray binaries. And that's something that we haven't been able to do before. So if we go back, our conclusion is that the X-ray binary low mass gap is actually a selection effect. And it does not need a step function for the supernova energy as a function of the progenitor. In fact, we have to allow low mass black holes to form, because we observe one now in 0529. We cannot any longer use ad hoc supernova prescriptions that forbid ever the formation of low mass black holes. That violates our gravitational wave observations. This is where 0529 lies. This is the mass range. It doesn't have an orbital period clearly. And the gap is not completely empty from the X-ray binaries. But the second conclusion, which is a little more crazy, although we're talking to supernova core collapse people and they're telling me it's not crazy, is that even if you forget whether black holes at low masses actually are born, let's say they're never born. If you accept, if you allow neutron stars to be born all the way up to the equation of state maximum limit, you're going to fill the gap in X-ray binaries, regardless of what happens with low mass black holes. You're going to fill it all the way up to 40%, 50%. So our secondary conclusion from this analysis, which we didn't expect, is that we're setting an upper limit to the birth mass of neutron stars, which has nothing to do with the equation of state. But it must have something to do with the explosion of and the formation of neutron stars. Am I betting my salary on this? No, I'm not. However, I will say that we did check and talked with pulsar observers, Scott Ransom especially lengthy, and we asked, we have pulsars that are 2.2 solar masses and 2.3 solar masses. They're all millisecond pulsars. So if you look at the young pulsars, the non-recycled pulsars, none of them are above 2 solar masses. In fact, most of them are below 1.7 solar masses. Okay. So that's where we are. This is our conclusion. And I'm going to leave it at this and welcome questions.
Thank you, Vicky, for the excellent talk. We have a lot of questions in the room. I just remind you, please use your seat mics before you ask your question. Yes, please go ahead.
Hi, great talk, very interesting. I'm confused about why in the modeling, assuming a maximum birth mass for the neutron star really matters, because if you make a cutoff, you're just saying, oh, at 2 solar masses, you're a black hole initially instead of a neutron star. So is there something different about the...
No.
Okay.
Yeah. So let me, I did go fast through some things. It's not that above 2 solar masses, you're a black hole. So I'm not saying that 2 solar masses is the maximum neutron star mass no matter what. What I'm saying is that if you are born as a neutron star and your mass is higher than 1.8 or 2 solar masses, then through accretion in a low mass X-ray binary, you will grow and you will grow and you will cross the equation of state maximum, which may be 2.5, 2.6, 2.7, I don't know. And you will keep growing. and you will even cross 3 solar masses, and you will feel the gap, the 3 to 5 solar masses. And how do we see this in our models? Is because we're plotting this filling factor, F-low, the filling factor, the percentage of systems in our population that are inside, that are transients, and inside the 3 to 5 black hole mass regime. We're plotting this fraction as a function of the birth neutron star mass, which could be all the way up to 3 to be completely safe. We don't know where the equation of state maximum is, but it's definitely below 3. And even for the Poseidon models or MESA models, if you start allowing the birth neutron star mass to become more than 2 solar masses, you start climbing and filling up the gap. Okay, so it doesn't mean that neutron stars above 2 are black holes. It just means that if I start massive, then I end up finding myself as a transient inside the black hole mass. I convert myself from neutron star to black hole eventually through accretion.
But otherwise, it would be a low mass X-ray binary.
Correct.
Okay. Okay.
Yes.
Well, Lika, I think, was first, and then Matteo.
Oh, sorry. Yeah.
I also wanted to multiple questions, but on the last point, does the fact that you need neutron stars to be born below 2 solar masses depend a lot on the stability criteria? Because I assume that you need a low mass star to accrete for long enough to actually accrete a significant amount. And if you would have like a high mass companion, you might not just have the time to dump enough without it just going completely unstable, or maybe, I don't know. I just wonder, do you need a lot of significant accretion during a common envelope, or is it all stable mass transfer? Or is it
no, this is stable mass transfer. So you are
a low mass companion.
Yes, because if you are a neutron star and your companion is a 5-6 solar mass, even intermediate mass star, you're gonna go into common envelope, and then you're gonna reveal the core, and then you're not gonna be classified as a low mass X-ray binary.
Yeah,
you would lose the envelope. If you're in the 5-6 category, you would come out, if it's a main sequence, you would end up with a merged product, no binary. If you're in the red giant, you would come out and you would be a neutron star, a little more massive. Maybe you accreted something in the common envelope, but not a lot, not half a solar mass or a solar mass. So you come out, you're still a binary, a neutron star, and you have a white dwarf next to you. And that is not a black hole X-ray binary.
And of the progenitor evolution, though, then, because so this, okay, and then I understood correctly that you need the companion to be indeed low mass, but then you had a previous event where you had the neutron star progenitor being
20 solar mass.
Yeah, 20 solar masses.
Yeah,
and a
15.
1 solar mass. And then they also probably interacted.
Oh yeah, you need the common envelope. I mean, that's how there you have 2 regular stars, and there's no way to form neutron star low mass X-ray binaries or black hole low mass X-ray binaries without bringing them together through a common envelope. Just like you can't form CVs unless you go through a common envelope, which was what Paczynski basically used to come up with the idea of the common envelope. Yeah.
When you ask a question, please identify yourself first to know who you are. Thank you.
Hi, Vicky.
Hi.
Thanks for a nice talk. Matteo here. Can you go back to Karim's plot? I think that's useful for.
Oh, was it at the end?
Yeah, that's it. Okay, so you convinced us that using your models, you can explain via selection effect the existence of a low mass gap in the observed low mass X-ray binary system. I was wondering, given your model that you built, it seems to me that you could extend it to a higher mass object and try it to see if you can actually reproduce the mass distribution of the higher mass objects. Have you tried that? And
we're working on it.
Okay, cool.
I mean, there is a paper from our Poseidon collaboration. I'm not a co-author, claiming, where my glass? So here. I think it's Gaia Black Hole 3, claiming that this one in the widest orbit is basically a black hole. It's very massive. It's a binary that never interacted, and that it can be done. The black hole is very massive. There was no kick. It was sort of the whole thing fell into a black hole. You know, it's not a very elaborate evolutionary scenario. I think the first author was Matthias Krakow. So yes, we're looking at all of them, but yeah, what I'm interested in is actually to have a self-consistent model for all of them. We're discussing the neutron stars and how to explain them. Look at the neutron stars, they're all below 2 solar masses. And those are young neutron stars. The companions are all main sequence, or double white dwarfs, which may be triples, and that's a whole other story. So yes, would like to, of course, go down that direction. We haven't done it. You can see some neutron stars here above the 2 solar mass line, and they're all millisecond pulses.
I didn't see who went first, but Jared, maybe.
Hi, for those on Zoom, it's Jared Goldberg asking. So can you go back to the slide, the last slide that you showed with the, that one. So the the birth neutron star mass is a prediction of stellar evolution codes insofar as it has to do with basically how big does your iron core grow before it collapses. So I know that Poseidon doesn't run things all the way to core collapse, but is it possible to like run a subset of those and ask what is the maximum neutron star mass? Because it might just be that they always get, I always find them get to 1.8 or, about that far, but it's hard to get.
I don't know.
So it seems like
I'll tell you, first of all, what we use here is the Sugbold and Patton 2016 and 20 engine for those who are experts. And the reason is that between the 2 Sugbold sort of predictions for compact object masses, the 2020 is tweaked to not form low mass black holes. Okay, so we use the 2016. We haven't done what you said. That's the simple answer. Partly because we're just busy doing other things and developing the code itself. I'm not eager to sort of go down that direction. I don't consider myself, a core collapse expert. Sure, we can take a small number of models, run them with the most elaborate nuclear reaction rates, go all the way to as close to the formation of the iron core, and see what we get. But we haven't invested that time. And also, I worry doing this in my group without a more expert collaborator. I mean, I always choose the projects in a way that I feel like I can catch mistakes if they happen. So I would rather collaborate with a core collapse expert before I go down that path.
Golden Barry. Sorry.
All right. Thanks again for the talk, Vicky. Will Farr for people on Zoom. I'm wondering how well you would say we understand the conservativeness of mass transfer from the main sequence companion onto a neutron star.
We don't.
Yeah, okay. So can you comment? I mean, when I look at the plot from Kareem's paper,
yeah,
it's striking to me how similar the mass distributions are between those low orbital period, presumably at least interacting neutron stars on the left side, and the large orbital period did not interact neutron stars on the right-hand side. I mean, you highlighted a few that go above 2, but barely. There's really, by eye, not that much difference between them. So what if mass transfer is simply insanely non-conservative? Just enough to make these systems become X-ray binaries, but they never, even over billions of years, gain much mass.
Yeah.
Is that a realistic picture?
Well, let me think before I answer with the obvious answer. I'm trying to remember if there is systematic evidence that the millisecond pulsars, which clearly have accreted, are more massive than the younger pulsars. And I'm going with a very vague memory, and I think there isn't, in the sense that you can bring a neutron star to millisecond pulsars with not a lot of mass accretion, quantity-wise. Okay, so having said that, I would say we know there are, if it's above Eddington limit, you're doing the, you're losing mass, you're allowing for non-conservative mass transfer, etc. If it's below Eddington limit, we assume non-conservative mass transfer. I'm sorry, we assume conservative mass transfer. We know there are stellar winds from disks. I'm sorry, there are disk winds. There's mass loss from disks. But we also know that there is accretion onto the neutron stars. That's how we get X-ray bursts, okay? So type 1 X-ray bursts. We also know in magnetic, we know we have polar accretion in magnetic white dwarfs in high mass X-ray binaries because we see hot spots, etc. So it's not fully non-conservative. Is the fully conservative assumption below Eddington the right assumption? What if it were 50%? Well, we did that even with 50%. And you can see what this is with the, I don't have the plot with Poseidon. You can see that you still grow up there. And you still, even with 50%, let me use.
But that growth is only ultimately an additional like 10% of gap filling.
But where are we with this one? This is the difference too. So with fully, this has an accretion limit too. Let me see if I have, I'm trying to find fully conservative. Yeah, so it makes a difference. Look at cosmic, okay, all right? So you go, this is fully conservative below Eddington. You go from 40%, and if you do it 50%, you go to a little above 50%. You accrete more, you move further. That's why this is. Yeah, maybe.
Okay. Yeah.
But then what I would say, I mean, I'm not arguing, it could be. I think there is some accretion efficiency. I don't think it's zero. I think if we make it 20%, I don't know that it would bring us down by 20 or 25% in here to bring us down here. If I go from 50% to 15%. And if I make it zero, then I put in my answer. what have you learned? Right? So if I assume in my population modeling that there is no accretion in the neutron star, I get out of my population that neutron star masses don't increase through accretion. Well, that's how I did it. That's how I constructed it. Yeah.
Barry, you still had a question?
Hi. Excellent talk, Vicky. This is Barry. So when you fill the lower mass gap from below by accreting onto neutron stars, is there a role for a kick at the formation of the black hole that could also assist in either unbinding the binary or making it wide enough that basically that will inhibit the population that's detectable as low mass X-ray binaries?
Depends on the kick mechanism.
Right.
If it is neutrino driven, but I think because we don't have the enormous mass m dots that we have in core collapse, these are very small accretion rates that pushes you over the limit. You're accreting over billions of years at about 10 to the minus, Eddington is 10 to the minus 8 solar masses per year, which is puny compared to what's going on in a core collapse event. I know, but the asymmetry compared to the inertia of the neutron star is not huge. And if you get a kick, these are low mass X-ray binaries. The orbital velocity of a low mass X-ray binary is 400 to 450 kilometers per second. So you would need a huge kick to change the orbit, which I don't think you get.